Hello, this is Mr. Gilmore with the 2.8 Pythagoras' Theorem. Now, as I had mentioned at the end of the last lesson, I am going to test you or quiz you over these two theorems, Euclid's theorem and Pythagoras' theorem. Now, in the 2.7 lesson, we saw how Euclid's theorem, in which he proved that there's an infinite number of prime numbers, infinite set of prime numbers. Today, we're looking at Pythagoras' theorem, which is his proof that the square root of 2 is irrational. Now, before we jump into this one, I'd like to tell you a little story about how this theorem unfolds. Now, of course, the truth behind this theorem, there's a little bit of truth behind it as far as what we know. How does the way the story ends, whether everything about the story is true, we're not quite sure. But in every culture, let's start here. In every culture, we tend to have some sort of revolutionary idea about numbers themselves. Like, for example, we kind of apply some abstract properties to numbers. So, for example, like in our culture, the number 13 would represent an unlucky number, whereas in other cultures, the number 8 would represent a lucky number, or in some, 8 is an unlucky number. And in others, 7 is a lucky number, and others, 7 is an unlucky number. So a lot of times we find that cultures will place some abstract kind of properties, kind of this revolutionary thought or entailment that attaches to some number. Well, let me tell you a little bit of history about Pythagoras. Pythagoras also had some of this cultural abstractness to his view of numbers. He believed that every single number, even the ones we already know are irrational, he believed that every single number could be expressed as a ratio of two others. So he began his journey into the adventure of the square root of 2. Right? They were familiar with what roots were, and he was familiar with the square root of 2, but he wanted to find out what were the two numbers that made the square root of 2 rational, right? So what two numbers could you bring together as ratios that would generate the square root of 2? And this is where he begins unintentionally proving that the square root of 2 is irrational. So let me jump into this and let's kind of show how square root of 2 is irrational. But there's kind of an end to this story I'll finish off later. So let's jump into Pythagoras' theorem, and we'll kind of finish where this story goes as he unintentionally proves that the square root of 2 is irrational. So here's what his proof states, right? Pythagoras' theorem states that the square root of 2 is irrational. Where we begin our proof is we do need to define a few terms, and we want to prove what's called a lemma. A lemma is a theorem, in other words known as a helper theorem. It's kind of like, let me prove something real quick about something we know to be true. Let's prove this real quick, and then let's use that later on in a proof. So it's kind of like laying the groundwork before we get into another theorem, before we get into another proof. Let's use this lemma to help us establish something we know to be true, and then we can use it in another proof. Typically, it's going to be more robust proof that follows the lemma. All right. So a few terms to define. The first is, what does it mean for a number to be rational, and what does it mean for a number to be irrational? Well, for a number to be rational, it then means that it can be expressed as a ratio of integers. So ratio of integers, think of our rational numbers. Any integer is a rational number. Any fraction is a rational number. Any negative fraction, any negative ratio, any repeating decimal is a rational number. An irrational number then means it's a number that cannot be expressed as a ratio of integers. Well, Pythagoras had this notion that every number ever to exist could be expressed as a ratio of integers, which is where his proof begins. He jumps into the square root of 2 is equal to a set or a ratio of integers. Now, before we get into the proof, we have to continue with some of our definitions. The next is the definition of what it means for two numbers to be relatively prime. So when I say two integers are relatively prime, that means the greatest common divisor between the two is 1. The only number that will then divide out of both the two numbers is 1. That would be what we call relatively prime. So for example, 2 and 7 are relatively prime. What is the largest divisor that goes into 2 and 7? Well, only the number 1 goes into 2 and 7, which means they are relatively prime. But if we look at the numbers 12 and 16, well, those are not relatively prime because there is the number 4, which is not 1. 4 divides into both those. That would be the greatest common divisor. So when we produce two numbers in which the greatest common divisor between the two is 1, that means we can call the two numbers relatively prime. Here's another fact. If we think of any ratio, any rational number, a rational number, any one of them, can be expressed as a ratio of relatively prime integers. What I mean, remember, when I say this word can, it means if I'm given any ratio, I can express them in a way that the numerator and the denominator are relatively prime to each other. That means that the greatest common divisor between our numerator and denominator values is 1, right? I know you can create fractions and ratios in which they're not relatively prime, but every ratio can be expressed as if the two are already relatively prime. So keep that in mind before we jump into this proof. Here's another fact. Let's say we look at any even integer that could be positive or negative, any even integer, and we're going to particularly start with our positives, okay? So every even integer can be expressed as twice some other integer. Think about that. If I think about the number 6, right, that's an even integer, I could express that as 2 times 3. Well, 3 is an integer, so it's twice another integer. And the converse of that is also true. That means if I were to give an integer, that integer really is twice some other integer, which means that integer is even, okay? So if an integer is twice some other integer, then it's even, so it works in the converse. Let's use some symbolism here and represent what this conditional and converse say. So in symbols, if I were to say if q is even, then for some integer k, right, which make up another variable k, to represent another integer, I could represent q as q equals 2 times k, okay? And the converse of that is also true, which means if I know q is equal to 2 times k, then k is, where k is an integer, then q is even, okay? We're going to see these facts used in Pythagoras' proof of showing that the square root of 2 is in fact irrational. Now on to our lemma. Now remember, a lemma is a helper theorem. So here's a conditional that we actually want to prove before we move on into our reduction, into our assumption and reduction of Pythagoras' theorem. So if the square of some integer is even, then that integer is even. So think about that. If let's give a integer, let's call it p. If p squared, right, is even, if p squared is even, then p also has to be even. So let's prove this lemma real quick. It's very easy to prove. So let's assume that the integer p is not even, which means p is odd. And if p is odd, that means p squared is odd because an odd times an odd is an odd. Well, we can't have p squared as odd because we were given that p squared is even, and that's a contradiction. Which then means we toss out our assumption, and what we're left with is our conclusion that our integer p has to be an even integer. So if we're given that p squared is even, then the integer p is also even, and we'll see how that applies in our proof of Pythagoras' theorem. Now on to Pythagoras' theorem. So I mentioned earlier this kind of little anecdote that Pythagoras kind of stumbled upon this because of his notion, because of his belief that every number can be expressed as a ratio of two integers, essentially meaning that every number is rational. Well, here's how the story ends. Okay, here's how the story ends. It ends up that Pythagoras, unintentionally proves that the square root of 2 cannot be a ratio of two integers, and it baffled him. He was enraged by it. He was mad about it, and so he kept going over his work over and over. He pondered it for days, that led into weeks, that led into months. He pondered over it, trying to wrap his mind around this notion that there are numbers that can't be expressed as ratios. So here's how the story ends. It turns out one of his students, again, this may be, we're not sure how this, if this is true or not, but one of his students underneath him suggested that maybe Pythagoras was right, because Pythagoras thought he was wrong. He totally thought he was wrong in his proof. But there was a student of his that suggested that he was right. Well, it turns out, let's just say Pythagoras and a couple of his buddies take this young young student of his fishing, and it turns out that let's say 6 men go on the boat, but only 5 men come back. So that's it. It was kind of crazy into the story of here of how passionate Pythagoras was in his notion that every number could be expressed as a rational number, as a ratio of two integers. So let's then take a look at how Pythagoras stumbled upon this. Well, here's how it works. Pythagoras is wanting to show that the square root of 2 is actually a ratio of two integers. Well, that's where our assumption actually begins, because we know that the square root of 2 is irrational, right? We're going to prove it's irrational, so let's assume that it is not irrational. In other words, let's assume that it is rational. So that means the square root of 2 is equal to some ratio of integers. Now we can go ahead. Remember, every ratio of integers can be expressed as if the two numbers are already relatively prime, the numerator and denominator. So then let's set square root of 2 equal to a divided by b, a over b, as a ratio, and a and b are relatively prime integers already, meaning that the greatest common divisor between them is 1. So keep that in mind. A and b are already relatively prime, because that is going to be something that's going to come into our reduction in the next step. So what can we do with now our assumption? If we assume the square root of 2 is equal to a over b, well, here's where we're going to be at. We're going to square both sides and then solve for a squared. So let's do this on the next slide. So here we have square root of 2 is equal to a over b. We are going to square both sides first and see where that takes us. So we square both sides, we get 2 is equal to a squared over b squared. Solving for a squared, we multiply both sides by b squared, and I'm going to go ahead and flip the equation around, so I have a squared is equal to 2 times b squared. Now, because we have assumed that a and b are already relatively prime integers, that means a squared is an integer and b squared is an integer. So take a look what's happening here. We have a squared is equal to 2 times b squared, which means it's an integer equals 2 times another integer. We can follow up with that. We then can state something about a squared. A squared is even. Why? Because we talked about some basic facts, that every integer, okay, if it is expressed as another integer times 2, then that integer has to be even. This is also where our lemma comes into play. If a squared is even, then we can say something about a. A is then also even. So what does that mean if we said a is even? Let's then go back to that basic fact that if there is an even number, it can be expressed as 2 times another integer. So since a is even, I can say let's let a equal 2 times some integer m, right? So m is an integer, right? Because we have declared a to be even. Well, what does that mean for us? Let's take this 2m and let's plug it back into our equation right up here, where we know a is equal to 2m. Let's plug it in for a in this equation here and see what unfolds. So we plug 2m in here, and what bounces out is something that looks like this. 2m squared is equal to 2 times b squared. Let's see what happens then after we square 2m. If we take 2m squared, we actually get 4m squared is equal to 2b squared. Well, I can then divide both sides by 2, and I get 2 times m squared is equal to b squared. Now think about that, okay? Think about that. I now have b squared, which remember is an integer, and we have m squared, which is another integer. So b squared is expressed as an integer times 2. What can I then say? I can then say that b squared is even. That goes back to that basic fact that if we have an integer that is that can be made from 2 times another integer, that integer has to be even. Well, then what does the lemma say about a square of an integer? If the square of an integer is even, then the integer itself is also even. Now, something has gone wrong. Take a look at what we just said here in our proof. By our assumption, since we assume that square root of 2 is equal to some ratio of integers, we've then said that A is even and B is even. But think back to what we stated in the very beginning. We let A and B are relatively prime, which means that the greatest common divisor between the two has to be 1. But if we just said that A is even and B is even, what does this statement mean? It means we found the greatest common divisor is 2. That right there is our contradiction. Since we assumed that the two numbers were relatively prime, we contradicted that, right? We contradict saying that they're not relatively prime now. That's impossible. That's absurd. And this is where Euclid's mind, he kind of trapped himself in this going, what just happened, right? I was trying to show that square root 2 can be a ratio of two integers, but it can't be. And he had to wrestle with that. He had to actually go against his own notion that all numbers can be expressed as a ratio of two integers. And so it really hit home, which is why he was very passionate about this and why it kind of actually drove him a little bit crazy that it turns out that yes, square root 2 can't be, right? Because of this contradiction, square root 2 can't be a ratio of two integers, which means it is irrational. And so thus begins kind of this introduction or this discovery of an irrational number. Now, I will post on Canvas the proof of Pythagoras' theorem, all typed up nice and neat in the chapter 2 module. Please be sure to go and check that out. I am either going again to test you over both of these, or I might just pick one of these to test you over. All right? But study both. Be able to reproduce them on your own. And if you'd like me for to check it, write it out. I would be happy to check over it, look over your proof, and give you some critique. So that is the end of our 2.8 lesson, Pythagoras Theorem. Thank you for listening and enjoying our little Pythagoras' anecdote. Again, I'm not even sure how true that is or what the truth behind it is, but a wonderful kind of story of showing how we prove that the square root of 2 is an irrational number, going from what we know of our basic facts of even numbers and of relatively prime numbers. If you do have any questions, please do not hesitate to email me. I will get back to you. Be good and do good.